Welcome back. In the last video, we finished off putting together the pieces of the puzzle with a VIT overview. We've broken down figure 1, we've broken down the 4 equations, and now we've had a look at table 1, which defines the different hyperparameters of different vision transformer model variants. And we discussed that we're going to be replicating VIT base because that way we can just start small, experiment quicker, and then if we want to upscale, we can do so. And I just added a little note here that the nomenclature in the paper is VIT-B, which stands for VIT base, so these hyperparameters, and 16 stands for an image patch size of 16 by 16, which is of course detailed here under model variants, and there we go. VIT-L16 means the large variant with 16 by 16 image patch size. So 16 is our patch size. And speaking of which, how about we start moving towards writing some actual code? To begin with, we're going to replicate all of these equations over time, that is. But to begin, we're going to start with equation 1, and that is the patch, position, and class embedding. So have a think for a second. How do you think we might turn our image, a single input image, into a sequence of patches? And then how might we embed them? You may have an idea if you've read through the entire paper, but if you don't, that's perfectly okay. You can almost guess if you wanted to. But I'm not going to reveal the secret yet. Let's instead see an overview of the VIT workflow. Now this is part of the visualize, visualize, visualize motto. Oh, we've skipped ahead. I've got a little animation here to overview what we're going to be replicating with code. So this is Food Vision Mini meets VIT. We cut it into patches. Now we have to embed each of the patches. Oh, we might embed it with there was a little spoiler there. It's a layer that we've used previously. And then if we embed each patch into a series of numbers, represent them as a learnable embedding. We've got 9 patches. There's another PyTorch layer we might have seen before. We flatten it to a sequence. That looks familiar, doesn't it? Then we've got the convolutional... Oh, excuse me. I've spoiled it. We've got embedding tokens. Then we've got class embedding, and then position embeddings in purple. We feed that to the transformer encoder layers. We feed the output of the transformer encoder layers to the MLP output. And then hopefully we get our class. So if we start again, I'm not going to rewatch this. You can watch this on your own time. It's also available in here. If we go, we've got a little overview somewhere. I believe it's in here several times actually. Yeah, there we go. So you can jump ahead and have a look at that. But we're up to equation 1. Split the data into patches and creating the class, position, and patch embedding. So let's jump in here. We'll start equation by equation. Equation 1. And this is going to be split data into patches and creating the class, position, and patch embedding. So what I like to do first is we've discussed previously that layers equals input and then some sort of function and then output. But what's another really important thing of machine learning? And I know that's kind of a general question, but when we have our input, it's some sort of representation, right? And so what's the input shape? We have a tensor, and what's its shape? And then the function does something, and then what's the output shape? So when I'm replicating a new architecture or trying to use an existing one, I always like to check out the input and output shapes of each layer, of the entire model, you name it. Input and output shapes. One of the biggest problems you'll find in machine learning and deep learning is misaligned tensor shapes. So let's begin by finding out the input and the output shape. Now, we kind of actually know what the input shape is. So the input shape will be a single image of 224, 224, 3. But what's the output shape of the patch embedding layer? This is equation 1, by the way. We're focused on equation 1. So this is single image which is, of course, height, width, color channels. Where could we get this information from? Well, if we go back up to section 3.1, it's described here. So let's copy this down, equation 1. I know we're doubling up here, but I'm trying to explain, as we've discussed before, some non-linear information in a linear fashion. So let's just take a little second here to read through this again, because this is going to give us our input and output shapes of equation 1. Once we have our input and output shapes, we can start to work backwards from there. So to handle 2D images, which is our input, in our case, we're going to start with inputting a single image, such as this image of pizza. You see what we're doing here? We're breaking things down into as small a piece as possible, a single input image and a single layer at a time. So we have X input is an element of a real number, height times width times color channels, 224, 224, 3, or in PyTorch it might be 3 first for color channels first by default. You can set it up so that it's this way though. Into a sequence of flattened 2D patches where X patch is an element of a real number of shape n times p squared dot c, where c is the color channel, and h and w, let's write this down, hey, while we're at it. So let's go, input image is h, I'm going to use, or maybe can I do this in dollar signs? I'm not very good at writing. I don't think this will come out nicely, will it? Maybe we can go times. This is experimenting on the fly here. Hey, there we go. So the input image is height, width, color channels. So I'm just going to put this down here, height times width times color channels. And where am I getting this from? Well, it's from right here. Now let's get the output image, or the output sequence of patches is of this shape. So we need to figure out what output image is $n, and then I'm going to go times, and then I'm going to go p. Oh no, I'm not quite sure how to get squared here. Maybe we'll just copy this, hey? Math B, we want this one. Beautiful. Might just get that there. And I can get rid of this R at the start. So we're just breaking this down step by step. And now let's go H equals height. I'm just going to start type. I'm not going to bother with the fancy text here because I'm much faster at just doing it like this. Color channels. Now N, what is N equal to? Let's find out what N is equal to, because we've got N here. N is equal to height times width divided by p squared, where p is the resolution of each image patch. So we actually know what p is now. We've said we're going to use a patch size of 16. So p equals patch size, and n equals height times, we'll write here, equals number of patches, equals height times width. We'll put that in brackets, hey? Height times width, and then we'll divide that by p and then squared. And then do we have anything else here? Uses constant latent vector size d. D equals constant latent vector size, which is also equal to embedding dimension. See table 1. Now that's just what we went through before in the previous video. So we've got all of the pieces of the puzzle here for the input and output shapes here. I just want to emphasize, yeah, there's the hidden size D. That's where D comes from there. So we don't actually want input image. It's going to be, we know it's an image, we just want the shape. So let's calculate it by hand. How do we start to do that? Well, how about we create some example values? Example values. So our input shape is height, width, color channels, and we know that the input shape is 224 of the image shape, And we're using colored images, so it's going to be 3 color channels, right? So height equals 224, width equals 224, color channels equals 3, patch size equals what? We've said that this is going to be 16. We got that from the model variant section. VIT-L 16 means large variant with 16 by 16 input size. And I believe if we go to, yeah, here we go. We've got some good results here from 16, 16. And then if we looked at the further results, if you read through the rest of the paper, VIT-B 16 performs pretty well across ImageNet. So it gets about 77 or 76% on ImageNet. So 1,000 classes, so that's pretty darn good. So this is what we're replicating. VIT-B, VIT-base with a patch size of 16. And we're trying to work out the input and output shapes of the first equation, breaking it down step by step. So we've got the height, the width, the color channels, the patch size. Now let's calculate by hand the number of patches. Calculate the number of patches. So number of patches, which is going to be n. We can use the formula here. We'll turn it into an int. We'll go height times width, because it needs to be a round number, that is. That's why we're turning it into an integer. And I'm going to divide it by the patch size squared. And so that is here. N equals height width divided by patch size squared. So we've just replicated that. Have I got one too many brackets there? Let's check out the number of patches. 196, beautiful. So that is going to be our n dimension there. So how can we work out p squared times c? Well, we can do that as well. Let's go, let's create an example input size. So input shape equals, we'll create the input shape and we'll go embedding layer input shape equals, what's this going to equal? So this is the input into our first embedded layer. So if we go back, we'll find figure 1. There we go. So we want the input shape of our image into our embedding layer. Oh, we've already got this, haven't we? Let's go back here. Is going to be height, width, color channels. Now, what's the output shape going to be? Well, we want embedding layer output shape is going to be equal to, we want number of patches times p squared dot color channels, or times color channels. So let's calculate this by hand. We'll go in here, number of patches, and then we'll go patch size squared times color channels. Let's see where this gets us, hey? Now you notice we've only got 1 comma here, so this is just going to calculate this there. So let's print it out and we'll go input shape. So this is going to be a single 2D image, and then we'll go embedding layer input shape, and then let's go print, and then we'll go output shape. This is of the embedding layer. Single 1D sequence of patches. So embedding layer output shape. Let's go. Beautiful, look at that. Now, where does this value come from? So we know this one, that's going to be our image size. And then we have number of patches. But this value, what does that remind us of? Well, that's from table 1. Hidden size D. Now you notice we didn't actually hard code that. That was inferred by the patch size squared times the number of color channels. Huh. So there's our embedding dimension. So The input shape of our first patch embedding layer is going to be a single image. And then to make sure that everything's correct, we've just calculated by hand what the output shape should be. A single 1D sequence of patches. Now, how do you think we get from this shape to this shape? So have a think about that. I revealed it in the little animation that we went through. So maybe you rewatch that, or if you want to skip ahead, there's some spoilers in the book here. But we're going to start moving towards creating this input and output shape with PyTorch layers. So with that being said, I'll see you in the next video.